What's up, little cinnamon buns? Welcome back to another beautifully designed, well articulated, beautifully proofread lesson about physics. Today, we're going to talk about the energy of a simple harmonic oscillator. You'll recall from the last video, assuming that you're watching these in chronological order, that we did an example last time about energy. But you know what I mean, you can never be too careful. So why do once what you can do twice? So we're going to talk about energy a second time today, and it's going to be beautiful. You know, someday, you guys, I'm going to learn how to set up pens before the video starts. And then nobody's going to be able to stop me. We're shooting straight to the front page of YouTube. Who's the biggest YouTuber right now? Ninja, I'm coming for your YouTube bucks. All right, let's talk about energy and simple harmonic motion. Okay, cool, let's go. So before we just kidding, you thought we were gonna talk about it right away. Not on your life. Before we dive into this very complex thing that you already know about, let's just remember a little bit of stuff about energy. So first of all, let's get a better color. What color do you guys want to look at? Red? Rojo. In a closed system, energy is conserved. This is like one of the most important energy principles you've ever principled in your whole life. Okay. The total mechanical energy is constant. This is a synonym for what I just said right there. So we just need to be aware. As long as the system is closed, meaning there are no external forces, then the total amount of energy is going to be the same the whole time. It might change what it looks like. It might turn from some kinetic to some potential or vice versa, but the total amount will be constant the whole time. So if we know one type, we can figure out the other type, which is going to be important for your homework and the AP test, and making cereal in the morning, and changing your car's tires, and picking out a new pet when you go to the pound. So the second thing we need to remember is energy transfers from kinetic to potential or vice versa. So if my kinetic energy goes down, my potential energy has to go up so that the total is constant. Okay, they've got to stay balanced. Yeah, that's all you gotta know about that. Mechanical energy is defined as the sum of kinetic energy and potential energy. Because these things just flip back and forth with each other, that's why this stuff stays the same. Recall, kinetic energy is just kinetic energy. Potential energy, we have two types that we could have. We could have potential energy of a spring, or we could have potential energy due to gravity, and they can alternate back and forth. Okay. The last thing we need to know is that when there is a minimum for kinetic energy, that corresponds to a maximum for potential energy, and vice versa. So if they ask you a question like, when does the object move the slowest? They're asking you about kinetic energy. There's no way the AP test is just going to give you that information. They've got to obfuscate it from you because they hate you and they want you to be unhappy. So what they're going to do is they're going to give you the potential energy, and then you have to know that they're conserved. So if this one's at a max, this one's at a minimum, and then you know when it's going the slowest, right? So just be aware that they're going to ask you about one of them. You've got to look at the other one and know about this relationship between them to be able to answer the question. So there's our reminders about energy. Okay, that's all the important like stuff that doesn't really fit into equations too well, but stuff we should know. Okay, it's qualitative facts about energy. Now let's dig into some equations real quick. We just want to be aware of these equations. We want to know what they are, have them written down somewhere ready to go so that when we're doing our homework, when it says how much energy does this thing have, and it gives you all the numbers for once in your life, you're not going to have to go find these equations. Okay, so write them down. Kinetic energy is 1/2 the mass times the velocity of said mass squared. Usually students forget about these squares right here. Don't be one of those students. The potential energy of a spring is 1/2 times the spring constant, meaning like how stretchy or stiff a spring is, times the displacement from equilibrium squared. And then good old potential energy due to gravity is mgh. Okay. Mechanical energy is equal to kinetic energy plus potential energy of a spring plus potential energy of gravity. These are all the mechanical types of energy. There's some other energies out there, but hopefully we don't have to worry about those too much. Okay, so now that we've remembered everything that Mr. Barton taught us about energy, let's go try and do some problems, shall we? Okay, so first one, we have a pendulum that is pulled 10 degrees to the side and then released. So let's draw this. Okay, pendulum, that, and then this angle right here, this angle is 10 degrees. Pulled that far and then released, the pendulum oscillates in simple harmonic motion. What a wonderful thing. And the length of the pendulum, L, is equal to 0.6 meters. How fast is the bob when it is in the equilibrium position? Okay, so how fast, we're looking for a velocity or maybe the absolute value of velocity, speed. And where is the equilibrium position? That's when the bob is hanging straight up and down. Okay. So this is actually an energy question. You're not going to be able to solve this by knowing about periods of oscillation and stuff like that. Because what happens is our bob starts with an initial velocity of 0 and then accelerates as it swings down until it's at a maximum velocity there. Then it's going to slow down as it rises back up the other side, and then you know how it goes from there, just simple harmonic motion. So let's talk about the energy of this problem. This bob, because we've pulled it slightly to the side, has raised a teeny tiny bit. They're not the same height. So because this mass has been lifted up, it has gravitational potential energy. So our energy initial here is going to be the gravitational potential energy. What we want to know is how fast it's going. So we're going to say our final right here is at the equilibrium position. E final, after the bob has fallen this distance, then we say that all of the energy, the gravitational potential energy, has been converted into kinetic energy. Okay, because energy is conserved in a closed system, we'll say the bob, the string, and the earth are all part of this system, then these things are equal to each other. So UG is the mass of the bob times G times H equals the kinetic energy, 1/2 the mass of the bob times the velocity of the bob squared. The great thing here is they don't tell us the mass of the bob, but they cancel out. See how it's on both sides? Divide by M, and there we go. So GH equals 1/2 V squared. Cool. All right. So we're looking for this velocity. So we'll multiply by 2 to get rid of this 1/2. 2GH equals V squared. And then to get rid of the squared, we'll take a square root on both sides. Okay. So V equals the square root of 2GH. All right. G we know. Well, this thing's on Earth. So G for us is about 10 meters per second squared. H. Okay. Here is the sticking point. And therein lies the rub, children. H is this unknown distance. And we're going to have to do a little bit of trigonometry to figure out what is this height of the, what's the word here? Of the, come on, you guys, help me out. The height of the bob. So let's talk about this. Okay. If we look at this bob here, let's clean this up a little bit. Okay. We're looking for this height. From here to here. So, do you guys see this triangle? This triangle? Okay. We want to know this distance here. This tiny little distance right here. That's h. Okay. But we can find it. So, let's talk about this bob. If it's at equilibrium, this height, this length here is L. Okay. It's gone up a little bit. This height, let's get one more color. This height right there, just to there, the whole thing's L. We're not quite at L. We're an H before L. This is L minus H, this teal line here. We can do trig to find this line here, and then we can solve for H. Okay, so let's figure out how long is this triangle here, this side of the triangle. So let's see, what sides do we know? We want to know this adjacent side here. Okay, we don't know this width here. We know this length. This length is L. And then we know L. L is 0.6. So let's set up, this is our hypotenuse, which is 0.6 right there. So we want the adjacent, we have the hypotenuse. What trig function uses adjacent and hypotenuse? That's cosine. So we're going to look at cosine of 10 degrees equals adjacent, which is y, over our hypotenuse, which is L. Okay. Now, let's grab our calculator. Where did you guys put my calculator? There it is. All right. So we're going to do cosine of 10. Cosine of 10, make sure your calculator's in degrees, is a number, right? It's actually 0.9848. Okay. Equals y over 0.6 multiply by 0.6 times 0.6 equals, so y equals 0.591 okay, meters. All right, so how high up is this? We found this thing here. Okay, it's 59.1 centimeters. The whole string is 60 centimeters. So the difference in them is going to be, what is it going to be? It's going to be H. So we're going to do L minus H. So distribute your negative, right? L minus L plus H. L's cancel, and we have H. So we're just going to do 0.6 minus 0.591. So 0.6 minus the answer. And we get a very small number. We get H equals 0.0091 meters. So it's like 9 millimeters-ish. Very, very tiny. But that's what it is. So here we go. Now we plug this in. At this point, we're just doing math, right? The tricky part was, how do I find H? We did it here. We have to do some trigonometry very carefully. Now we just plug in our numbers. So we have the square root of 2 times 10 times 0.0091 equals V, and we're home free. So it's the square root of that number times 20. And V equals 0.427 meters per second. That's actually pretty fast, right? You've got something 60 centimeters long. You give it a little tiny deflection of 10 degrees. And now this thing's going almost half a meter per second. That's pretty quick for a thing just swinging back and forth. So, cool. Very good. That was fun. I show you this for a couple of reasons. One, because I really love math. I really love digging into these equations and looking at triangles and I wonder how I could measure that. The second is because I think there's a question on your homework that's going to require you to look at H, and you kind of have to do some trigonometry. So just be aware. If you get stuck, let me know. But fun question. So we're just conserving gravitational potential energy and kinetic energy. And bada bing, bada boom, we know how fast the bob is going. So, all right, cool. Fun problem. Let's look at another one. Okay, this is the other really big, I guess, archetype of problem that you're going to see on the AP test when it comes to analyzing the energy of a simple harmonic oscillator. They're going to give you a data table. They recorded some information, a data table. Hopefully they made a graph so it's nice to look at. And they're going to ask you some questions about the oscillator based on these data points that they recorded using either a timer or a position sensor. What do you call those things? Motion sensors. So we've got to understand how to look at some data and pull out the information we need. So it says the graph below shows the position of a mass 2 kilograms attached to a spring with a spring constant of 100 newtons per meter as a function of time. So you've got this thing. Presumably they displace it and then it oscillates back and forth. Here is the position as a function of time. So they put like a motion detector here. And then whoop, 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 detect the motion. Here's our graph. This is not what they did because you see how it oscillates around 0. That probably wouldn't happen. It would probably oscillate around like 0.2 or something. So that, because 0 would be at the motion detector, negative would be over there where it can't sense. So that's not how they did it. Maybe they did some video analysis or something, which is possible. But they got this graph either way. So they want to know, does the period of oscillation measured match the expected theoretical value? What does that mean? It means they want us to calculate the period of this system using an equation and compare the answer we get to this graph. So let's do that. The period for a spring simple harmonic oscillator is 2 pi times the square root of m over k. M is the mass, which is 2 kilograms here. K is 100. So we're just doing 2 pi times the square root of 2 over 100. And then I've already plugged this in. Where did I put it? TS equals 0.8886 seconds. Okay. So the period, meaning the time it takes to do a full oscillation, is almost 0.9 seconds. So let's go look at our graph. Here's t equals 0. Here's the displacement axis. We want a full oscillation, which means it has to go all the way up, come back. So that's all the way out, come back, oscillate all the way over here, and then come back one more time. Okay, so we end up right there once we've completed 2 full oscillations. Here's 1, here's a half. That's about 0.8, yeah. So this graph looks pretty stinking close to what we would expect, right? We don't have an exact number. They might want to give us a data table or something. That would be nicer. But it's pretty stinking close, right? If we kind of draw a line through this graph right there, that's about 0.8, 0.9. Pretty close. So sounds good to me. Okay. At what time would the kinetic energy be a maximum? Okay. So this is maybe a slightly less straightforward question. Because this is oscillating, there's a bunch of times this would happen. This happens multiple times. So let's talk about our energy really quick. In this, when our system is stretched, so here's equilibrium, here's the max. When it's stretched, and this is at rest, it's gone out, it's slowing down, it stops right here, and it starts to come back. Here, all of our energy is tied up in potential energy of a spring. Once it comes back, once the spring pulls this back towards equilibrium, it passes equilibrium. Here, the force is 0. And we've converted our potential energy into another type of energy. That type of energy here, once our box is at equilibrium, the energy here is kinetic. Because we're at equilibrium, this spring is not stretched, so we have 0 potential energy due to the spring. So anytime our spring potential energy is 0, our kinetic energy is at a max. So when would this be at 0? The equation for the potential energy of a spring is 1/2 kx squared. K is not ever going to be 0. It's a constant. It's equal to 100. So the only thing that can be 0 to make the potential energy 0 is this stretch from equilibrium. So anytime we're at equilibrium, then our potential energy is going to be 0. So where are we at equilibrium? Here is displacement. Here is the furthest it ever gets. Here is the closest it ever gets. Equilibrium is always right in the middle of these two spots. So our equilibrium happens here and here and here and here. So any of these times would be suitable. They'd be our time. What exact timing does our kinetic energy reach a maximum? So here's the full period of 0.8886 seconds. This, if you know anything about sine waves, this is half. So our kinetic energy is going to be a max at t equals n, which is the fancy math variable for an integer. So 1, 2, 3, 4 times t over 2, right? Here's half t, here's 1t. Here's 1.5 t, so n equals 3. Here's 2t, 4t over 2, right? So this is when our kinetic energy will be a maximum. It's every half period. So there you go. Pretty interesting, pretty good stuff. Energy oscillating back and forth. Yeah, so good luck. Have fun analyzing those graphs on your homework. We're done with notes. You did it. You survived. Short one this time, only 24-ish minutes. So make sure you do your homework. Make sure you eat your vegetables. Make sure you pet your dog and take out the trash like your mom asked. Otherwise, have a wonderful day, everybody. I'll see you guys next video.